Section 4, we start by designing an advanced machine learning model. In this video lecture, Ensemble Learning Theory, we continue what we have started in Section 3 when we discussed bootstrap aggregation. In this section, we dedicate our discussion to other types of ensemble learning, which is named boosting. Boosting is similar to bagging in that it combines many weaker models together, but it differs in how it combines them. Boosting trains a tree and then uses the samples that failed on the first one to train another tree on them, and so on till it arrives at minimum error possible. The resulting model is a cascade of decision trees, where each one is trained on the errors of the one before it. Boosting excels in many applications, especially ones that bagging and random forest fail in predicting correctly. The reason why boosting excels over bagging is that it is based on an objective function, which makes it mathematically flexible enough to handle many tasks in both classification and regression. One of the most popular models in online data science competitions is XG boosting. There are a few disadvantages of boosting since it is more sensitive to noise and subsequently more prone to overfitting than random forests. CART method handles missing values either by imputation with average, either by rough average or the mode, or also by an averaging mode based on proximities. However, one can build a gradient boost model or random forest with other type of decision trees. The usual replacement for CART is C4.5, which was proposed by Quinlan in the 1990s. In the C4.5, the missing values are not replaced on the dataset. Instead, the impurity function, which we have discussed in very deep detail in section 3, the impurity function computed takes into account the missing values and penalizes the impurity score with the ratio of missing values. The following discussion is dedicated to gradient boost algorithm. Gradient boosting is a machine learning technique for regression and classification problems, which produces a prediction model in the form of an ensemble of weak prediction models, typically decision trees. It builds the model in a stage-wise fashion like other boosting methods do, and it generalizes them by allowing optimization of an arbitrary differentiable loss function. The idea of gradient boosting originated in the observation that boosting can be interpreted as an optimization algorithm on a suitable cost function. So gradient boosting is interpreted as an optimization problem. We take up the weak learner and at each step we add another weak learner to increase the performance and build a strong learner. This reduces the loss of the loss function, and then iteratively we add each model and compute the loss. In using this loss value, the predictions are updated to minimize the residuals. So gradient boosting is actually the combination of gradient descent and boosting. So in order to understand what gradient descent is and how it works, we look at the equation on the screen right now. We define a loss function, which is here notated as j of some variable. The loss function j, the objective is to minimize the loss, arrive at the minimum loss possible. So once the problem is known to be a minimization problem, it can be solved using a gradient descent that is a very simple minimization algorithm. Now it's time to discuss one of the concepts in machine learning, which is named cross-validation. The cross-validation is important for evaluation of the models and how much they have learned from the training data and how well they can generalize to new data samples that were not used for training. So we understand that the standard cross-validation divides the data into k-splits, and k-1 of them are used for training and the remaining one is used for validation. This is then repeated until all the subsets have been used at least once in the training and testing. This way the model takes advantage of all the samples available in the dataset. Cross-validation is ideally used to find the best fit model, which is then elected to be used for full training on its own. It can also be used for hyperparameter optimization. Cross-validation is also useful for obtaining more realistic error measures, since k error values are obtained instead of only one. The time series data is often strongly correlated along the time axis. Randomization will make it likely that for each sample in the validation set, this defeats the very purpose of having a validation set. The model essentially knows about the validation set already, leading to inflated performance metrics on the validation set in case of overfitting. On the screen right now, we have a graph displaying these different techniques of cross-validation. You can imagine each line as the timeline. You can imagine the blue blocks on one line of them, not all of them, just one line of them, is the training set, and the orange blocks are the test set. So in the first case, at the very top, the case of cross-validation, we can see that we are using the test set chosen at random. So we can see that there are 5 lines. Each line of them is one instance of randomization. The third idea, block cross-validation, sounds more reasonable since less data points are omitted.